Hello everyone, welcome to the class once again. I hope you're all doing good and you're the best of your health. So I believe that you have watched all the previous session of this chapter, electric charges and field. And last class I was discussing about Gauss theorem. I gave you a brief detail about and an idea about Gauss theorem and how to apply it. Today's class you'll be seeing about more applications of Gauss law and the significance of Gauss law. We'll start with significance of Gauss law, how it can be used and where it is utilized. Let's begin with significance of Gauss theorem, or you can say Gauss law. I've used the term Gauss theorem every time. Significance of Gauss theorem. Now, one thing, this is required while using the Gauss theorem, the thing that I'm going to tell you. First of all, I told you there will be charges distributed and we have to actually enclose the charges. That is what, if I say that there are so many charges in space, let's say Q1, Q2 and let's say Q3 and n number of charges may be there. So first of all you have to enclose these charges with any closed surface. So remember, it's applicable only for closed surface. If the surface is not closed, we cannot apply. So what we can write that it's true for closed surface. First point. Next thing, let me tell you, first of all you see there are charges enclosed. Now there may be charges outside also. If I say there are charges outside Q4 and Q5. We have in the Gauss theorem formula, we have that electric flux is equal to Q upon epsilon naught. We have in the Gauss theorem integration of E dot ds is equal to Q upon epsilon naught. The charge coming on the right hand side should be considered only the inside charge, that is the charge whichever is present inside the Gaussian surface. We need not to consider the charge which is present outside the Gaussian surface. So remember, in the right hand side of the equation, Q upon epsilon naught, the charges present inside the Gaussian surface should only be considered. Charges present inside the surface should only be considered. Inside the surface should be considered, and we should not take into consideration the charges which are present external to the surface. Charges should be considered. Next thing, then what is the significance of the charges which are present outside? Have they got any role to play or do they have no role to play? Let's talk about the charges which are present outside. Now, in the left hand side of the equation, you have that integral E dot ds. Let me write on the equation and let me tell you what I mean to tell you. E dot ds, this is the electric flux, is equal to Q upon epsilon naught. This is Q inside, Q in, I'm writing upon epsilon naught. This is what the Gauss theorem equation states. Now, in this equation, if you see that this is the electric flux, which I have talked about, integration E dot ds, which I have already given you in the last class. This electric flux is not only due to the internal charge, rather it is due to all the charges present. That is, external charge is also taken into consideration when we talk about the electric flux. So if the question comes, the electric flux that you calculate, is it only due to the internal charge or it is also due to the external charge? So electric flux is also due to external charge and including the internal charge. That is, it's due to this charge Q1, Q2, Q3 and Q4, Q5. In statement, if I write, electric flux is due to all charges, not only due to internal charges, it's due to all charges. So don't think that only internal charge have got a role to build the electric flux and external charge has got no role to build electric flux, rather they have also got a role to play. The only thing, because their net effect of electric flux building, that will come out to be 0, but yes, it also builds up the electric flux. Net electric flux that we have here, this is due to all the internal and external charges, but we consider, while calculating, we consider only the internal charges, because its effect, the external charge effect, will actually add up to 0. Next thing, how carefully you have to think about a Gaussian surface. I have told you that you have to enclose the charge. Now, why are we using Gauss theorem? There are certain applications of Gauss theorem. We'll be seeing that it will be continuous, a uniform distribution of charges. So to actually enclose them, you have to draw a uniform surface. If you draw a surface randomly in this way, then it will be difficult for you to apply the Gauss theorem. It's better to draw a surface which uniformly encloses all the charges present. So fourth point you can write, the Gaussian surface should be uniform. See, remember I am saying this as a point. You can draw Gaussian surface in any way as you want. Even this is also a Gaussian surface. But the limit actually it will create, the constant that it will build on us, we will not be able comfortably to solve the electric flux, and applying the Gauss theorem, it will be difficult for us to use such kind of surface. The surface should be uniform, and that should uniformly enclose the internal charge. The Gaussian surface should be uniform it should uniformly enclose the internal charge. It should uniformly enclose the internal charge. Uniformly enclose the internal charge or internal charges. We'll talk upon this. We'll use, and I'll tell you how to draw actually Gaussian surface. We'll actually talk upon this. Next thing you see that if I talk about one more point about that, you need to take caution. Now see, these are discrete charges. Q1, Q2, Q3, Q3, these are discrete charges, point charges present somewhere in space. There are two types of distribution of charges. Either you may have discrete charge distribution or you may have continuous charge distribution. In continuous charge distribution, charge will be present everywhere within the object. But in discrete charge system, point charges are present randomly in space. They can be placed anywhere, they can be. So if I talk about how to form the Gaussian surface, what precaution you should take, what thing you should avoid. For a discrete charge system, never pass a Gaussian surface through the charge particle. This caution you have to take. Gaussian surface should not pass through discrete charge, should not pass through discrete charges. You know why? Because when we define electric field, when we have given the value of electric field is given at some distance, and its inverse square, its dependence is on this inverse square on the distance measured from the point charge. But at the point charge, if we cannot give the value of electric field, so we cannot draw the Gaussian surface passing through the discrete charge. So Gaussian surface should not pass through discrete charges. But remember, in this one more point, in this only one more point you can add that in the case of uniform distribution of charges, in the case of continuous distribution of charges, the Gaussian surface can pass through the charges system. But in the same point I am writing one more thing. In case of continuous charge, in the case of continuous charges, Gaussian surface can pass through charges, Why is this so? Because the charge is actually distributed continuously within the object, and we will be seeing its application. Why in discrete charge system we cannot pass it? Because electric field cannot be given at any point charge, but in case of continuous charge system we can actually let the Gaussian surface pass through the continuous distribution of charges. This was all about that the precaution that you need to take care while drawing Gaussian surface. Some important points and which we will be using in this lecture, in this topic. Now, after giving you such details about usage, about the significance of Gauss theorem, let's proceed with the application of Gauss law. So if we need to use where to apply applications of Gauss law. Now Gauss law, this can be used at many places. Wherever you find a continuous distribution of charges, you may use to evaluate the value of electric field due to that charge system. So application of Gauss law, we will be actually using Gauss law to find out the electric field due to continuous distribution of charges. So where it will be used? It will be used to find electric field due to various continuous distribution of charges. So find electric field due to various continuous distribution of charges. Right now I'm saying continuous. Wherever applicable, we can also use it for discrete system of charges. That is also we can do, find electric field due to continuous distribution of charges. Now how will be using it? Continuous distribution of charges. How will be using it? The method, the steps employed are very simple. How will be using it? Steps used or steps employed to find out the value of electric field by using the Gauss's theorem. The Gauss theorem, the first one, the first step, you have to think of a Gaussian surface that uniformly encloses the charged object. It should actually enclose some uniform distribution of charges compared or related with the object, whichever the object contains. First of all, you have to do, you have to draw such a Gaussian surface which uniformly, so draw such a Gaussian surface which uniformly encloses charges. The continuous charges, it has to actually uniformly enclose the continuous charge system. Then what you have to do, you have to think that at a particular distance the electric field is constant. Then for that particular Gaussian surface, you have to find out the integral of E dot ds. So what you have to do, or what for the next step you can employ, the second step, within this Gaussian surface, check how much charge is present. So find charge present within the Gaussian surface. Find charge present within the Gaussian surface. This is the second step that you can do. You have drawn a Gaussian surface. Remember, I am using a term Gaussian surface. It's nothing special about when I use with a surface a term Gaussian. It just implies that you have actually drawn a surface which is actually uniformly enclosing the continuous charge distribution. So find charge present within the Gaussian surface. Third step that you can employ, third step will be find integral of E dot ds, and you have to equate it to charge enclosed upon epsilon naught. Fourth, equate integral of E dot ds to q inside upon epsilon naught, and then finally you will be getting the value of electric field at that distance with respect to the object. This is what you have to do in case of finding the electric field with respect to a uniform distribution of charges. So let us go ahead with the first application of the Gauss's theorem. I have given you the steps. Draw such a Gaussian surface which uniformly encloses charges. Second, find charge present within the Gaussian surface. Third, find E dot ds. Fourth, equate E dot ds, that is equal to q in upon epsilon naught. Now after this, after learning about the basics of Gauss theorem, let's go ahead and let's apply application of Gauss theorem and find out the value of electric field with respect to some charge distribution. First one, electric field due to uniformly charged thin wire or uniformly charged rod, you can say. So electric field due to infinite line, electric field due to infinite line of charged wire, or infinite line of charge, you can say infinite line of charge. Instead of wire, you can say infinite line of charge. Now charge is uniformly distributed, so let me draw a infinite line of charge and let me see how to evaluate the electric field due to this infinite line of charge system that we have. Now see, infinite, that means it will be continuous, it's very long compared to the distance where you need to evaluate the value of electric field. It will be very long, and already we have done this while calculating the electric field. Already we have done this in the previous sections, but I will tell you now how to apply Gauss law to find out the value of electric field due to this line charge distribution. See, this is the charge distribution. Already for a finite wire, for a finite charge, we have evaluated the value of electric field for a finite wire, and then we increase the length to find out the value of electric field due to infinite charge distribution. Let's say plus charge is distributed uniformly all over its length, plus charge distributed, and let's say charge per unit length, is given as charge per unit length, this is equal to lambda. Let us say this is equal to lambda. So lambda is the charge per unit length for this uniformly infinite line of charge, uniformly charged infinite line of charge. Suppose we want to find out the value of electric field at a distance r here somewhere. At this point P, we are interested to find out the value of electric field at a distance r from the wire. Now I told you the first step should be draw a Gaussian surface which encloses the charges. So here you think that what kind of Gaussian surface you can draw. If you draw a sphere, it will be a problem for us. That will not be uniformly, because every point on the circumference, on the periphery of the sphere will not be uniformly located compared to the wire. It will be better for you to draw a cylindrical structure so that which may behave as a Gaussian surface. See what I am going to do, I am going to draw a cylindrical surface in this way, which is going to enclose the charges in this way. So here you see I have drawn a cylindrical surface which has a radius small r. Its radius is given as small r. Now it's enclosing a charge. Let's say the length of the cylindrical surface is given as L. The length of the cylindrical surface is given as L. So first step we followed that, draw a Gaussian surface, we did it. Second step, find the charge present inside the Gaussian surface. Second step, so charge inside the Gaussian surface. Charge inside the Gaussian surface, if I talk about Q in, that will be equal to lambda into L, because lambda is the charge per unit length and L is the length of the cylinder, so lambda into L will be charge inside. Third step we have to do, we have to actually find integral of E dot ds. So E is what? You have to think that E is the electric field at a distance r. Now this is a very long wire, it's this wire, if you think, it's very long wire, it's continuing top to bottom. This length is so long that this length will be very small compared to the length of the wire on which the charge is present. So you can think that the electric field will be in this way everywhere. This is how the electric field will be. Now if I see this top circular surface and this bottom circular surface, electric field will be passing parallel to the top and bottom surface. That is what you can imagine, that is what you can think. Electric field will pass parallel to the surface. Now let's talk about integral E dot ds for the entire Gaussian surface that we have drawn. E dot ds that is what we have to evaluate. So third step, integral E dot ds. Now see that this electric field and area vector if I take a small area ds, area vector and electric field both are parallel to each other, and electric field can be taken as uniform everywhere. Its value to be same everywhere. If I talk about electric field, its value to be same everywhere, because we are actually evaluating it at the same distance r from the wire, at this distance r. Now E dot ds, if we evaluate, is uniform, and for this circular surface, the curved surface of the cylindrical, the area is 2 pi r into L. 2 pi r circumference into L, that will be the area. So this will come out to be E into 2 pi r L. We evaluated third step we did. Fourth step, equate this E dot ds with q in upon epsilon naught. This is what I have told you in the fourth step. When you equate it, you will be getting E into 2 pi r L is equal to q in, that is lambda into L upon epsilon naught. L and L will be cancelled out, which I am showing you here. So finally, electric field comes out to be lambda upon 2 pi epsilon naught r. This is what you will be getting about the electric field for this infinite line distribution of charge. We have actually evaluated the value of electric field. Next thing you see, how we have done, we applied all the 4 to 5 steps for this, and we evaluated the value of electric field due to this infinite length of wire. Now its direction is away. If I give a unit vector along this direction, and let's say this unit vector is n cap, so electric field in proper vector form we can write electric field is equal to lambda upon 2 pi epsilon naught r n cap, where n cap is the unit vector directed perpendicular to the line of the wire, perpendicular to the line wire. That is what we have shown you. That is, this is the n cap, that is the unit vector along this line. Next, let's go ahead. So you can think about, imagine as a pencil, and it's a pen, it's a long rod you can imagine, over which the charge is present. Second application, electric field due to plain sheet of charge. Electric field due to plain sheet of charge. This is also can be evaluated using Gauss law. We will be very quick in doing this. Already we have learned the method how to evaluate. So let's do very quick. Due to plain sheet of charge, let's try to find out the value of electric field. Plain sheet of charge, so it's a charge will be distributed over its entire area. So let's say the charge per unit area is given as sigma. The charge per unit area, this is equal to sigma. So if I have a plain sheet of charge, how can I draw it? I can draw it in this way. Just you may think that this drawing may sometimes disturb you, but it's okay. Till the time you get the idea what I'm drawing, it's okay. This is a sheet that I have tried to show you all here. Don't worry about the drawing, just think that it's a sheet. Charges are distributed all over the area of the sheet. Now it's a very long sheet, it says the uniform distribution of charges will be same everywhere at the front side, at the back side. Now if we want to find out at any distance from it the value of electric field, so what I need to do, we need to draw a Gaussian surface. I am going to draw again a cylindrical Gaussian surface for this infinite plane sheet of, already I am showing that it's crossing this, but you have to think that it's passing through. See what you how you need to imagine. Let's say if I have a copy over here, and let me show you. This is the infinite sheet. This is a copy over this infinite sheet. Charges are present all over its surface, and the same charge distribution at the both sides. You need not to imagine the thickness of the surface. This is a Gaussian surface that I actually have. Actually, it is passing through this, and it's present on the two sides. That's you can imagine. The center it's going, it's present on the two sides. Now, next thing, how to find out the value of electric field? Let's say the surface area is A over here, and you see there are two surfaces. One plane surface, surface area is A, which I have shown you here, and one curved surface. This is the curved surface. Now see that first point, draw the Gaussian surface. We have drawn a Gaussian surface for this particular charge distribution. We have drawn the Gaussian surface. Next thing you see, we need to find out charge enclosed within the Gaussian surface, charge inside. That's very simple. Charge inside can be very easily evaluated. You see that sigma is here. Sigma is the charge distribution, sigma is the charge per unit area. If you see the charges present, that will be sigma into this area A, because A area will be passing through this part. This will be also A area. So charge inside will be equal to sigma into A. Next thing we have to do, we have to find out E dot ds. So just evaluate E dot ds. Now again think that electric field vector will be along this direction, away from the charges. Electric field vector, if I show you here, it will be along this direction. Now see here, electric field and area vector for this curved surface, that will be perpendicular. Area vector will be perpendicular for this curved surface, so E dot A will be a 0 for curved surface. Now talk about this surface, the circular surface. Area vector will be in this way and electric field will be in this way. For this side, if you see for this side also, area vector will be directed along this direction and electric field vector will also be directed along this direction. That is what we can say. So electric field E dot ds, if I need to talk about, you have to take 0 E dot A for the curved surface, but for this plane circular surface, this side and this side, you can say that E dot A will come out to be 2E into A. Electric field will be at this distance will be same, E and E at the both sides. So 2E into A, then you have to equate E dot ds is equal to Q in upon epsilon naught. This is what you have to do. And just be very fast. So E dot ds Q upon epsilon naught. So we have to write 2EA is equal to Q in, that is equal to sigma into A upon epsilon naught. So E comes out to be sigma upon 2 epsilon naught. This is the value of electric field for this charge, this infinite plane sheet of charge that we have taken. Remember, I am saying it's a big plane sheet of charge. I am not saying it's a thin conducting sheet of charge. I am not saying that. I am saying it's a infinite plane sheet of charge. For it, you are finding the value of electric field. Now here I have shown you electric field flux for this curved surface is 0. You have to consider the flux only to this surface. And the flux, now see in the last case, when we are doing for the line charge, the flux for the upper circular surface, that will be 0, which I have not told you separately, but you should also note that in the last one, in the line distribution, for the upper circular surface, the area vector will be directed perpendicular to the surface and electric field is parallel to the surface. So both area vector and field will be perpendicular to each other. You will be getting electric E dot A as 0 in that case also. So like in curved surface here, in that the plane circular surface, you will be getting electric field flux as 0. So two formulae you have to learn. Electric field is equal to lambda upon 2 pi epsilon naught r for the infinite line distribution of charge, and electric field in the case of infinite long plane sheet of charge, it will be sigma upon 2 epsilon naught. So till for this class, let me wind up here with all this information. I'll be continuing with more concepts in the next class. Till the time, wish you all the very best and thank you everyone.